Potential due to a point charge. So the change in potential when a charge Q moves from point A to point B is going to be given mathematically as VB minus VA equals UB minus UA over Q naught, or Q over 4 pi epsilon naught 1 over RB minus 1 over RA. Now what happens if you take the reference point at infinity? Then UA will become RA equals infinity, which is going to give you 0. Or 1 over RA goes to 0, and we are left with Q over 4 pi epsilon naught 1 over R subscript B. Then we drop the B, and we are left with this equation. So here's a very interesting idea. So when you look at this picture, I want you to picture this by itself, sort of. So a positive charge sitting by itself. And you want to figure out what is the potential as you go away from this positive charge on either side. Well, you will note that as you go away from this positive charge, the potential will become smaller and smaller and smaller until at infinity it becomes almost 0. However, as you come closer to this positive charge, the potential will go up and up and up until at x equals 0, v goes to infinity. Okay? So potential for positive charge is positive everywhere. Similarly, for a negative charge, same thing happens, except the potential is going to be negative for this. But it follows the same pattern as it does for the positive charge. Now, what about potential due to a collection of point charges? So in this case, what you do is you calculate the potential at a point P, because let's say we want to find the potential at point P, due to each charge as if the others were not present at all. And then simply add the resulting potentials to get the total potential at point P due to any number of charges. So now let's do an example. Suppose that we want to find the potential due to the 3-point charges as given in this picture. Okay? What do we have to find? We have to find the electrical potential at point 1, 0 due to the T charges. And then a point charge, point 5, moved from a great distance to point A. What is the change in electrical potential energy? Okay, so in this scenario, let's first draw a picture. It's asking me what is the potential due to these 3-point charges, Q1, which is 4 microcoulomb located at 0.3 centimeters, Q2, which is 2 microcoulombs located at 1.0 centimeters, Q3, which is minus 3 microcoulomb located at 2 centimeters. So first of all, let's try to figure out where this system would look like, what the system would look like. Okay, so first of all, Q1, it says, is at 1, 2, 3. So Q1 is going to be here. Q2 is at 1, 0. So it's at 1, 0. That's where Q2 is. And Q3 is at 2, 2. So it's sort of somewhere here. Okay, that's Q3. Then it says, where do we actually have to find it? We have to find it at point A. So this is where I am trying to find the potential. We just talked about this. We said that the potential difference, the total potential difference at point A will be given by the potentials for each one. I'm going to just call it R1 plus KQ2 over R2 plus KQ3 over R3. We just talked about it. We're just going to calculate the potentials from each one separately and then add them as if nothing else was present here. Okay? So what is R1? R1 is easy, right? That is just 2 centimeters. So that one's easy. So I can write R1 as 2 centimeters. Okay? R2, on the other hand, is this distance here. How do I find this distance? Well, this is 1, so it'll be 1 squared plus 1 squared, which is square root of 2. So this is square root of 2 centimeters. Okay? And Q3, or R3, will be this distance here. So how do I find this? That is this, and that is this. So what do I get? It is actually equals to 1 centimeter here and 2 centimeters here. So R3 will be 2 squared plus 1 squared square root, and the answer is 5 square root, or 2.33 centimeters. Once we have all of these numbers, all it's left to do is to plug them in, solve for it, and I get plus 1.863 times 10 to the 6th volts. Now, why is this important to recognize whether this is plus or minus? The reason why it's important to recognize whether it's plus or minus is if this sign is A, it means A will have, point A has positive potential energy. So what that means is to bring a positive charge from infinity to point A, potential energy must be increased, hence positive work must be done by an agent bringing the charge. Okay, so that means I'm going to rewrite this for you. To bring a positive charge from infinity to point A, potential energy must be increased. So a potential energy must be increased. This implies that your external agent or external force, whatever is bringing this system together, must do positive work. Okay? Now, for part B. So this was part A. Now for part B. It says a charge of minus 5 nanocoulombs moves from infinity to point A. So now instead of A being empty, it now has 5 nanocoulombs of minus charge on it. Okay? What would be the change in electrical potential energy for the system? So what is the relationship between electrical potential energy and the delta V? Yes, so change in potential energy will be Q delta V. Okay? Which means this is going to be Q V final minus V initial. So what was V initial? Absolutely, it was infinity. So this means this goes to 0. At R equals infinity, potential is 0. What are we left with? Q V final. And where are we going to find the V final from? Absolutely, answer from part 1. Okay, so the change in electrical potential energy will be 5 minus 5 nanocoulomb, which is 10 to the minus 9 coulombs. And VF is going to be this number here, plus 1.863 times 10 to the 6 volts. Okay, multiply them together, and you get minus 9.3 times 10 to the minus 3 joules. That is the change in electrical potential energy from bringing a 5 Newton charge from infinity to this point. Another example, this is very interesting. It says 4 equal positive charges are fixed at a corner of a square of side S. Is the electrical field 0 at the center of the square? Is the potential 0 at the center of the sphere? Now, we are going to use, in order to answer this, symmetrical arguments. Okay? So electrical field, remember, has to start and end at certain points. So if you have an electrical field and they are all pointing towards in, let's say they're all positive charges, so they'll all be pointing in. So at the center of this kind of an arrangement, where will these fields line up? Nowhere. So the electrical field inside this square will be 0. On the other hand, is the potential 0 at the center of the sphere? Remember, potential is a scalar. So if this is a scalar, then the potential cannot be 0. However, what would it actually be? It will be potential in this case. So you have these arrangements. Potential in this case in the center. So part A, E field will be 0, because where would it point, right? E is a vector. Where would it point and where would it end? So E is 0. However, potential is not 0 at the center. But what would it be? V, I know, is KQ over R. Yes? In this case, how many Q's are there? 4. So the potential at center will be V1 plus V2 plus V3 plus V4. Yeah? Scalar? There are 4 of them, so it will be 4 V's. Yes? Which will also equal 4KQ over R. And what is R? R is actually, if this is S, so this is S over 2, what would R be? So that's a quick, dirty math. R will actually be equals to, for each one, S over square root of 2. Once you plug them in, 4KQ over S over square root of 2. And that's your answer. So some other important concepts that we should all be aware of. One is called an electron volt. What is an electron volt? It is the energy required by a particle of charge E when it moves through a potential difference of 1 volt. So an electron volt also is equals to 1.6 times 10 to the minus 19, but the unit for electron volts is going to now be joules. Okay, this is a very, very small amount of energy, and it's on a macroscopic scale. But electrons in a typical atoms have few electron volts of energy, right? So, but on a macroscopic world, it's a very, very tiny amount of energy. So Van de Graaff generators are some of the applications of potential. So I hope you've all played with this or seen this. If not, just type in Van de Graaff in Google and it will show you hair-raising experiments that people do. Potential difference in biological system. So if you were to look at a neuron, the action potential is the graph between potential difference inside and outside the cell membrane at a point along the axon as a function of time. So in a nutshell, what do you need to remember about electrical potential? Well, electrical potential and electrical energy are related, but they are not the same. Electrical potential difference is the work per unit charge that must be done to move a charge from one point to another without changing its kinetic energy. Delta V is equals to delta U over Q naught, which is equals to minus work done from B to A divided by Q and 0. The terms electrical potential and potential or potential difference are the same thing. The only differences in electrical potential and electrical potential energy are meaningful. It is always necessary to define where U and V are 0. Hence, we define V to be 0 at an infinite distance from the sources of the electrical field. Sometimes people also define V to be 0 at Earth, and we call it ground. It should be clear from the context of the question where V is to be defined as 0.